Hello physics students, this is Dr. Berenzi, and this is lesson 7.1.3. Our objective for today is that we're going to be able to interpret stress and strain graphs to determine when a material is elastic and when it is plastic. Now there are a lot of new words in there today. We know what stress and strain are from lesson 7.1.2, but we've never seen it drawn on a graph before, so that will be a new experience for us. And then there are a couple new words, elastic and plastic, which I need to define for you so that we can attain our objective today. So, let's begin. All right. So let's suppose that you have an object subjected to some form of stress, and then you decide to remove that stress. So one example is to take an empty Diet Coke can and you decide to put it under some sort of stress by applying force here and here. And by the way, if you remember last lesson, what type of stress is that? Well, hopefully you remember that that's a compressive stress. So we're putting this Diet Coke can under compressive stress, and we are going to figure out what happens after that stress is removed. Well, you can imagine that one of two things is going to happen. And here are the two options. One is that the Coke can returns to its original shape, or over here on the right, our Coke can meet a more tragic fate and end up being permanently deformed, and it has no hope of ever recovering its shape ever again. Well, the option on the left, when a material is able to return to its original shape, that is a material that's behaving elastically, or we can call that behavior elasticity. On the other hand, when the object becomes permanently deformed, it does not return to its original shape, then we just say that the material is behaving plastically, or that that's an example of plasticity. So any material can behave with elasticity or with plasticity. Well, what's the difference? When does a material behave like this, and when does a material behave like this? Well, when we put a stress on this Coke can that is small, very, very small, like you're barely just like pinching it to lift it up, well, you are placing a stress that is really small. And you'll notice that once you put that can down, it returns back to its original shape, and that Coke can has behaved elastically. It is exhibiting elasticity. In yesterday's class, or in our last lesson, we learned that there is a linear relationship between stress and strain. As a matter of fact, one of the examples, like for compressive stress, we found out that stress divided by strain is equal to a number, and that number is called the Young's modulus for most materials. Well, this Young's modulus happens to be the slope of this graph. And you'll notice that the more stress we place on the material, the more strain that material is going to have. So if we put twice as much stress, we are going to get twice as much strain out as we did in a previous trial. Okay, so we have so far been talking about materials that behave elastically. But what if we decide to up the stress, to put more stress on it? And what's going to happen to this graph when we put more stress on it? In other words, where does the graph go from here? Well, it turns out that if you decide to put more stress on it, that graph is going to start looking something like this. So we start off down here, and this is the part of the graph that we observed so far, where our stress is fairly small, and so is our strain. But what happens is that if you put too much stress on it, what's going to happen is that this graph no longer becomes a straight line. In other words, there's no longer a direct proportion relationship between stress and strain. It now becomes nonlinear. And what happens is something very interesting. You don't need to put a lot more stress on it to get the object to exhibit a lot more strain. So it's, in a sense, starting to behave a little bit like taffy. You just put a little bit more force on it, a little bit more stress on it, and it's going to actually stretch out quite a bit. Now, what if we decided to release the stress right here? So we have applied more and more stress and observed that the strain at first has a linear relationship, but then at some point it becomes nonlinear, and we decide, okay, we're done with our test. What is going to happen to our object at this point, our soda can? Well, if we decide to let it go at this point, what's going to happen is it's going to try to recover. It's going to try to come over here, but it no longer can. So what it's going to do is actually it's going to settle down, and it's going to end up with a new set point. In other words, it's going to have a different length permanently than what it did before. And here on out, this is going to be its new length, and unless we put some other type of stress on it, there's no way that it's going to recover. So that's one really interesting behavior about materials when they behave plastically, is that they never return to their original shape. If we started off with a certain length, we're going to end up with some extra length or a shorter length, depending on what type of stress you're talking about. I guess in the case of the Coke can, you would actually end up with a smaller length than what you started with. Just like right here, we've let go of the pinching, the compressive stress, and this Coke can is not going to recover from that. It's going to be thinner than it was before, and there's nothing it can do about it. Sorry, Coke can. Now, something else interesting happens. If we were to decide to keep on applying more and more stress, or actually to keep applying that stress and not let it go, what eventually happens is that it will eventually actually hit a breaking point. So at some point, the strain becomes so large that the material decides to break in two. And on this graph, the people who made this graph labeled this rupture, but you can also call it fracture, or you can call it a failure. It all depends on which engineer you talk to, I suppose. They all are synonymous. Now, I want to finish up this very short lesson by talking to you about a few features of this graph that you're seeing here and define some terms that you're going to see in some problems come tomorrow. Okay. Now there is an area of this graph where the material behaves like an elastic. In other words, it's going to recover as long as we don't exceed this amount of strain right here. Then this material is going to recover and return to its original length after we have let go of the stress. Okay, so this is an elastic area in a sense. Okay, now you'll notice, if you look very carefully, that there is a limit just before this happens where the relationship between stress and strain is no longer linear. So even though this graph is starting to turn a little bit like this, it can still recover and go back to its original length, even though it is starting to no longer have a linear relationship between stress and strain. So this stress, where it no longer behaves linearly is called the proportional limit, because after that, stress is no longer proportional to strain. Now, if we let the strain get too high, we have passed what is called the elastic limit. And for most materials, the elastic limit happens at a strain that is around 0.01, somewhere on the order of that. It could be 0.03, 0.04, but somewhere around 0.01, most materials encounter what's called an elastic limit. Once you have gone beyond this strain, this material is no longer going to recover back to its original length if we decide to relieve the stress. So if we get into this territory and then I suddenly let go of the stress, I relieve the stress, if it reaches this point, it is never going to be able to get back to here. What it'll likely do is it'll probably follow a line that's parallel, and it might end up with a small permanent change in its length. Now there is a stress beyond which you cannot go without breaking our material, without fracturing the material. And that stress is what's called the ultimate strength of the material. So you might hear of an aluminum rod has an ultimate strength which is equal to 10 to the 10 pascals. Okay, what that means is that if you exceed that stress, you are going to break that rod, no matter what. So once you get beyond the peak right here, you have exerted a stress on it that it can no longer recover from, and it is going to break. That breaking point is called the fracture point. It is the amount of strain that it will be able to stretch out to before it finally decides to snap. Okay, so those are some terms that are very important to remember or to know for working with stress versus strain graphs tomorrow. And we are going to have problems that are talking about the proportional limit. And that's the amount of stress that you can't exceed and still have stress proportional to strain. And then we're going to be talking about problems where it gives us the ultimate strength of a material, and we have to calculate how much force we need to put on it, or how much force can we put on it, and other problems like that. I think they're pretty straightforward. If you are pretty familiar with your stress versus strain problems from yesterday, I don't think you're going to have any difficulty with these. You just need to know some extra vocabulary, which is why I'm not going to put an example on this one, but we will work with plenty of stress versus strain problems when we come back to class again next time. All right, physics students, hope you found this educational, and I look forward to seeing you soon. Bye.